Well, if you work in manufacturing or quality, perhaps you've been in this situation. You are responsible for a manufacturing process that is not operating properly, and you don't know why. But you're getting lots of help from material suppliers, operators, engineering, and the maintenance team. There's no lack of experts. And there's no agreement on the solution as there are so many variables, and you are not sure which ones to turn, which knobs to turn, if you will, nor in which direction. At the same time, your boss is very excited about the high scrap and the poor yield, and you need some help to proceed. So I want to welcome you to the Practical Problem Solving Clinic, Problem Solving Experimental Techniques, Part 1. So this is Part 1 of 5 parts of this series to take you through hypothesis testing and designed experiments. I'm Mike Vella, and I'm recently retired after 42 years in operations and quality, 30 years with an automotive OEM supplier of safety critical parts, and then 12 years with a food manufacturing company. I've got an undergraduate degree with Western Michigan University and MBA with Wayne State University, and that's in Detroit. I'm a senior member and fellow of the American Society for Quality, and there I was certified as a quality and reliability engineer. Experimentation techniques is one of the modules in our practical problem solving package. So as you saw in the previous slide, the practical problem solving package has 6 elements. First is structured problem solving, the 8D method or the 8 discipline method. Next is an introduction to statistical process control, SPC. Following is understanding variation to solve problems. Then ongoing control. The subject of this package, experimentation techniques, and focus on the process. So the objective of this training is to provide you a working knowledge of a few statistical tools to help you make decisions and solve problems. So in part 1 of our practical problem solving package, learning about statistical experiments, we're going to be discussing the purpose of statistical experiments and give you an introduction to hypothesis testing and designed experiments. So the purpose of statistical experiments is pretty straightforward. It's knowing versus thinking that you know. Thinking that you know is called opinion. Knowing that you know is fact. In manufacturing, we often use statistical experiments to help us improve quality and productivity. If you're operating a process, it's not unusual for you to see some variation in the production. You'd like to know if a change in the process has occurred or if what you're seeing is just random variation. In addition, you'd like to know how to control a process. You'd like to know which of the process inputs actually control the process output. Driving a car, it's pretty simple. You turn the wheel counterclockwise, the car turns left. Clockwise, the car turns right. So you know the steering wheel input left, right changes the attitude of the vehicle. That's the same kind of control and certainty of control you'd like to have with your process. You'd also like to know how much each process input contributes to a given result. Is it a lot or is it little? And you want to determine the effect of any planned change on the process. There's oftentimes ideas that people may have to improve the process. You'd like to know, is this change going to be a significant change or not? Again, statistical experimentation allows us to know how a process works instead of thinking that we know a process works. So a DOE, or a design of experiments, and hypothesis testing are statistical methods which improve the efficiency and reliability of process improvement and problem-solving process efforts. While other methods are available, none compare to these statistical techniques for arriving at the right answer in the least amount of time and at the lowest cost. What we want is, like on the right, fast, cheap, and good. Hypothesis testing is a statistically valid test of a hypothesis which models an observable process and a set of random variables to determine if the process is changed. Example, suppose it is expected that a supplier's new raw material will have a positive effect on the production yield. By conducting a test under controlled conditions and evaluating those results using statistical tools, we can state with a specified rate of error that the process either improved or did not. A test of hypothesis will determine whether the results obtained during the trial will carry over into day-to-day production. Different than a hypothesis test, a design of experiments is a planned information gathering exercise where variation is present and the effect of changing levels of specifically selected variables, which are thought to affect the results of your process, are evaluated. When working for quality and productivity improvement, we use designed experiments. The best results start by working closely with those most familiar with the process being investigated. That's the team closest to the process. Production operators, production supervisors, quality technicians, maintenance people, and engineers who work with the process every day. Sometimes a facilitator is used to organize the team and to summarize their thoughts about the process factors and what they think the process setting should be that will make a difference in the product. This designed experiment can be performed to actually determine which of the factors actually make the difference and what settings these factors should be made. Here's an example. Your batch production team has conducted a brainstorming session and has identified 5 potential changes which they consider will provide a positive impact on process yield. So this is thought to be an industrial process, but consider this process being one where you're making a cake in your kitchen. First one they think is adjusting the temperature of the batch. Second, adjusting the amount of time the batch is mixed, how long the batch should be mixed. Third is changing to an alternate supplier of a key ingredient. Fourth, changing the speed of the mixer, fast or slow. Fifth, changing the order of how the ingredients are added to the batches. These are their thoughts. So of the 5 process variables the team has developed, how do we know which, if any, of these process variables are important? How do we know to what degree they may be important? How do we know the optimum setting of each important process variable? And how do we know which combinations of those variables might work together to produce a better result? There are other types of experimental techniques beyond hypothesis testing and designed experiments, and they're commonly used for problem solving in manufacturing operations. Unfortunately, they all lack efficiency. They cost too much and take too long. They're not reliable, and they produce inconsistent results. The techniques I'm talking about will be trial and error studies and one-at-a-time studies. So let's talk a bit about trial and error experiments. Perhaps you've been on the production floor, you've been in the Gemba to see one of these trial and error processes work. First, someone decides to change some process factor. They then decide if any improvement has occurred. If the desired improvement has not been achieved, they make another change to a different process factor. The first change may or may not have been set to its original setting. Then they evaluate the result and continue to change and test and change and test and evaluate the results until the desired performance is achieved, if it ever is. So let's talk about problems with trial and error. Trial and error can be time-consuming and therefore probably expensive. You're going to have downtime, scrap, and experimental costs that weren't planned for. Trial and error lacks structure. There's no guarantee that when you're on the production floor and someone is suggesting, why don't we change this variable or that variable, that you haven't run that set of experiments before. Trial and error results often depend on the experience or the intuition or the opinion of those people who are running the experiment. That is, they don't have the insight and vision of a team to help guide the process. Those that use trial and error often emphasize the trial part and not the error part. Well, let's talk about one-at-a-time experiments, sometimes known as the engineering approach to problem solving. One-at-a-time technique assumes that a single golden screw exists, and that single golden factor controls the entire process output. One-at-a-time experiments are often used by those with lots of experience with on-the-fly experimentation. They probably have never told you about the many experiments that didn't go well. Success of one-at-a-time depends on holding all other process controls perfectly constant while the experiment proceeds. Now, theoretically, you could say, well, while the process is going to be conducted, the experiment is going to be conducted over a short time, but what happens likely is this experiment will last over multiple shifts, multiple days, multiple weeks, and you know process variables can't be held constant during that time. As a result, there are many possibilities for undocumented changes without the team's knowledge, and therefore unlikely and unreliable results. Here's the method. Try to hold all factors constant while changing only one factor. Then, evaluate the effect on the process. Proceed to the next factor and then repeat. Continue until all factors have been changed to their new level and all the effects have been evaluated. Again, sounds good, but simply doesn't work well. One-at-a-time experimentation looks at the factors individually and not in combination with the levels of other factors. As a result, this methodology is inefficient, slow, and expensive. It's never able to understand the relationship between interactions between factors. And as I mentioned before, it is highly unlikely that you can hold all the other factors constant while you are repeating trials over time. If you believe that, you're simply fooling yourself. So use of designed experiments, or DOE, greatly reduces the number of trials and samples needed to make an informed decision. DOE provides the ability to see interactions between factors. More knowledge is derived with less effort and less costs. And unlike other types of experiments, the chance of making a decision error can be quantified. In summary, there are several ways to conduct investigations of manufacturing problems which involve many variables with unknown contribution. Their effectiveness is not equal in terms of time, money, and reliability. The most efficient way of investigation and solution of these problems is to use statistical techniques such as hypothesis testing and designed experiments. Let's talk about Hypothesis testing. We'll go through the general concept, we'll talk about something called a test for means and a test for proportions. The general concept. Well, maybe this is the wrong general. That's a great picture of General Patton. Wrong general. Hypothesis testing. The most straightforward form of statistical experiment that can be run on a process is called a test of hypothesis. Many other types of statistical methods, such as control charts and design of experiments, are derived from this basic concept. And that is, we want to know if the process has changed or not. Hypothesis testing is a technique that is used to determine if a change is made on a process, materials, methods, labor, environment, and has that change produced a significant effect on the product. The method looks to answer the question, are things different or are they the same? For example, suppose you made a change to a process intended to increase productivity. Well, the first month's production shows that there's an increase or decrease in output. A test of hypothesis will help you determine if the effect is real or simply a chance occurrence which might reverse itself in the following month. We want to know for sure. Hypothesis testing can be used to distinguish between the performance of two machines, two methods, suppliers, or operators. Suppose you need to determine whether supplier A or supplier B provide a similar quality component. A test of hypothesis can provide this direction. But before we proceed, let's have a little discussion about samples and distribution. In another video that's posted on the web, it's called Describing and Controlling Variation, SPC, we learned that process streams exhibit patterns of variation that form distributions. You see the distribution on the right, sometimes called the normal distribution. The distribution parameters that interest us are the center and the width of the distribution. If we draw samples in a random manner from a well-mixed population, sample averages will form a distribution of values. Recall from that video that the central limit theorem says that sample averages form the normal distribution. No matter what the parent distribution look like, sample averages form the normal distribution, and that's important because we know how the normal distribution operates. We know the normal distribution has a curve that's similar to the one you see, and if you break apart the width of the distribution into equal segments and define them as called the standard deviation, we know that plus or minus one standard deviation from the center will find 68% of the individuals or averages. Plus or minus two standard deviations from the center will find 95% of the individuals or the averages. And plus or minus three standard deviations from the center, you'll find 99.73% of the individuals or the averages. When talking about quality and quality improvement, we want to reduce variation. Quality is best defined as minimized variation around a targeted process stream. So when we take a look at these two distributions, the one on the top and the one on the bottom, clearly the one on the top is producing from a process that has given you better quality than the one on the bottom because the distribution is narrower. The parts are more and more like each other than not. Minimize variation around a targeted process stream is a definition of quality. So many people look at process performance as an absolute. In this case, the process is running as 0. Is that right? The absolute view of the process considers that all the results are stacked up at a single point. That's not really the case. In the absolute view, it is easy to evaluate change. Any value which does not match our concept of absolute value signals a shift in the process. While this view of the world is simple, it's wrong. In the real world, we know that there is variation associated with every process, and that variation falls into some kind of process distribution. For example, in this case, the process average is 8. It's between 7 and 9. And the standard deviation is 2, centered around the mean. Plus or minus 3 standard deviations from the center range between 8 and 14 on the right, and 8 and 2 on the left. In a statistical view of the process, it's more difficult to evaluate whether a change has occurred. We ask the question, have one of the process parameters shifted? Since we seldom know what the true values of the distribution parameters, we address this question through sampling. We must decide whether an observed change in our sample statistic in response to a planned or suspected change in the process is due to an actual shift in the parameters or the result of the laws of chance. The question becomes, has the process really shifted, or have we simply sampled from a different part of the same distribution? For example, if we consider process at time 1, green distribution, and process at time 2, we describe a shift in the center of the process. If we sample in the area of overlap between these two distributions, how do we determine from which distribution the sample came from? So how do we use a sample to show if a process parameter has shifted? The answer is we use what we know about random samples and attach probability values to the different values of our sample statistic. So a sample drawn from the original green distribution on the average will produce a lower estimate of our mean, our X bar, or average, than a sample drawn from the red, the new distribution. The odds of a sample reflecting the overlap between the two are very small in comparison. If you're familiar with the statistical process control methodology, we use a control chart to do the same thing. Using the rules of control charts analysis we learned in describing controlling variation video, we know that 7 points in a row on one side of the average or the other indicates a shift. So you see the arrow pointing to the left is the original process, and you see a shift in the process in the arrow pointing to the right. That indicates a process change. What about the tails? The distribution has tails. What if, through the laws of chance, we draw one sample from the lower tail of the distribution and a second sample from the upper tail of the distribution? What might we conclude? Well, assuming we've drawn random samples, the odds of selecting two samples, one that reflects just the lower tail and one just the upper tail, is very small. It's much more likely that both samples will come closer to reflecting the actual or mean or the center of the distribution. So again, the general concept of hypothesis testing looks at the odds of arriving at all the possible values for the sample statistic for both the original process and the change process. Using a simple test, it helps us decide whether our given value is more likely to occur under the original set of conditions or a changed set of conditions. So we have a number of steps, 8 easy steps for us to perform a test of hypothesis. Step 1. Formulate in words the theory or hypothesis that you wish to test. Second, state the theory in statistical terms. Step 3, state in statistical terms what conclusion we will reach if the theory turns out to be false, and discuss what the alternative is. Step 4, set a margin of error for the decision. What are the consequences if we make a wrong decision? Step 5, select an appropriate sample size. Step 6, choose the test statistic and formulate the decision rule. Step 7, select and measure the samples and calculate the test statistics. And step 8, make the decision based on the criteria which was formed in advance of the test. Don't worry, we'll go through some examples. Before that, we'll have a bit of terminology. Hypothesis is a proposed explanation for a phenomenon. It's a theory or assumption made about a process parameter. For example, we propose that if we make a change to the new, cheaper supplier of baking flour used to make our breakfast buns, we can maintain productivity on the number 2 baking machine at 1,000 buns per minute, but at a lower cost. It's a picture, it looks like, of Egg McMuffin buns rolling down a conveyor. So the null hypothesis, something we're going to call H, hypothesis 0, is the hypothesis that we wish to test stated in statistical terms. A typical statement would read, the null hypothesis, HO, is mu, which is the average, equals 1,000. That's the population average, center. This might mean we wish to test the theory that the process is producing an average of 1,000 buns per minute. The null hypothesis is often known as the innocent hypothesis. Accepting the null hypothesis says that nothing has changed, nothing is different. The null hypothesis is the innocent hypothesis, compared to the alternative hypothesis, which represents our decision if we have evidence based on the test that justifies rejecting the null hypothesis. For example, the HA, or the hypothesis alternate, is that mu, or the center of the distribution, is not 1,000, or that the alternate hypothesis is that mu, the population average, is less than 1,000. Stated in words, the process is not averaging 1,000 buns per minute. The process is averaging less than 1,000 buns per minute. Rejecting the null hypothesis says that something has changed, that the process is different. For example, let's talk about inspection. If we view the component material inspection process as a test of hypothesis, the null hypothesis is that the items inspected conform to specifications. Items inspected are innocent, if you will, until proven guilty. The alternative hypothesis is that the items inspected fail to conform to specification, and that is we should reject or rework the parts. Let's talk about a little bit of a matrix. So on the top, possible true state for the items, parts are either good or the parts are bad. On the left, possible inspection results, we either accept or reject. So if the parts are good and we accept them, that's a correct decision. Another correct decision is that the parts are bad and we reject. The other two are errors. So the inspection process can be viewed in this matrix: possible true statements and possible inspection results, 2 possible correct answers, 2 possible errors. 2 types of errors, again, we're talking about terminology here, can be made. A type 1 error is the mistake of rejecting the null hypothesis when it is really true. We're going to give this type 1 error, it's noted by a symbol called alpha. And when drawn in something called an operating characteristic curve, which is seen on the right, the type 1 error typically is at 95%, 0.95, and less than 1, usually 0.5. A type 2 error is the mistake of accepting the null hypothesis when it is false. So type 1 error is the mistake of rejecting the null hypothesis, the innocent hypothesis, when it's really true. And type 2 error is the mistake of accepting the null hypothesis when it's really false. And we're going to call that beta error. And beta error is seen down on the right-hand side, the lower arrow. Here is that same error matrix we saw in a previous slide. When the null hypothesis is true on the top and the null hypothesis is false, the decision rule will either accept the null hypothesis or reject it. So 2 ways to make a correct decision is when the null hypothesis is true and we accept it, or the null hypothesis is false and we reject it. Two ways to make errors. Type 1 error is when the null hypothesis is true and we reject, and the type 2 error is when the null hypothesis is false and we accept. How about an example? I don't know how many of you have been on a jury before, but it's a very interesting civil duty that I would encourage you to take when called on. But let's suppose you're on a jury and a man has been accused of murder in your state, which supports capital punishment. Well, the reality is just twofold. Either the man committed the murder or he did not commit the murder. The possible outcome of the trial for the accused is to be pronounced that the person is guilty as charged or not guilty, and the person is going to be released to the public. So in this case of you're on the jury, capital punishment, the reality is either the defendant did not commit the crime or committed a crime. And you on the jury have to determine whether the person is guilty or not guilty. Again, there's 2 ways to make a correct decision depending on the situation. If they did not commit the crime and the jury finds him not guilty, correct decision, you free the defendant. On the other hand, if they committed the crime and you found them guilty, good decision, okay to execute. On the other hand, the type 1 error comes in the case where they did not commit the crime, but the jury found them guilty. And the type 2 error is if they committed the crime and we released the individual to the public. So a type 1 error is made if we reject the null hypothesis of innocence when the null hypothesis is true. A type 1 error would lead you to executing an innocent man, rejecting when the person is really not guilty. A type 2 error is made when we accept the null hypothesis of innocence when the defendant is really, in fact, guilty. We would be releasing a murderer to walk the streets, maybe to kill again. So as a member of the jury and knowing that errors will always be made, Which mistake should we as a society wish to avoid the most? How would this decision change if we were trying the alleged murderer in a state without capital punishment? This kind of thought process is used in hypothesis testing for determining the appropriate risk of test error. In summary, hypothesis testing is the simplest form of statistical experiment. To use this technique, we must view the decision-making process in statistical terms and determine if a change has occurred. We make this determination by following the general method for performing a test of hypothesis. So I'd like to thank you for your time and attention in viewing part 1 and ask you to proceed to part 2, where we will continue our discussion about hypothesis testing. We'll talk about testing for means and testing for proportions. So I'd like to acknowledge the Greater Detroit section of the American Society for Quality Control for their introduction to me of hypothesis testing, which was done when I became a certified quality engineer back in 1978. And later on in this study, we're going to be working with designed experiments and the Taguchi methodology. And I wanted to recognize the Ford Motor Company and their work with the American Supplier Institute, introducing Genichi Taguchi and Yuen Wu and their work on what they call offline quality control, and to Mr. Tom Dole for his enduring work in training and continuous involvement in the training process.